Welcome back to the 17th video about the full fly-by-wire electric outboard project. In the previous video, about 3 weeks ago, we started with the redesign of the analog to digital converter's front end. Mainly because there was a fatal flaw in it regarding the reference voltage, but we also used that opportunity to improve other things. Card here, link in the description. Now I've got the required parts, and so we can start to implement those improvements in this video. Enjoy! Short recap of what we talked about in the previous video and what in the end I decided to do to improve the front end of our analog to digital converter. The main problem was that I put too much load on our reference voltage source, and thus the reference voltage broke down, became unstable, and that led to a number of funny effects. But we also identified some weaknesses in our temperature measurement, our voltage measurement, and our current measurement front end. The temperature measurement circuit had too high of an output impedance for our analog to digital converter. The battery voltage front end wasn't using the whole dynamic range of our ADC. The current measurement front end had both flaws. It has a little too high output impedance for our ADC, plus it wasn't using its full dynamic range. Here are the solutions I choose from the alternatives we discussed in the previous video. And a big thank you to Busy Electrons for providing feedback on those alternatives. First, we buffer now our reference voltage using an op-amp to create a buffered reference voltage rail that can take the load and doesn't break down. Second, the current measurement front end is now a differential amplifier, also based on an op-amp, which increases the dynamic range we are using in our analog to digital converter and solves the output impedance problem. Please note, the output stage of the op-amp we are using here, the TLV9144IN, has a rather large headroom. For our motor current measurement, that doesn't matter. We can drive the output up to 2.5 volts. No problem, our supply rail is at 5 volts. But in the future, if we want to measure negative currents, for example when charging the batteries, we cannot fully drive that down to ground. There will be a headroom of about 250 millivolts, which is about 5 amps. So we can only measure down to minus 45 amps, but that's okay. Third, the front end for our battery voltage measurement is now also a differential amplifier with a little protection Zener diode here at the input, just in case we have some overvoltages. And that differential amplifier allows us to use, of course, more of the dynamic range of our analog to digital converter. Please note, with that circuit we again run into the headroom issue. So we expect here voltages at the input between 15 volts and 30 volts, and 15 volts would drive that down to ground. However, with a headroom to ground of 250 millivolts, that will cut off 1.5 volts. So we can really only measure down to 16.5 volts, which is okay, because our lithium iron phosphate batteries will switch off at 20 volts or so. Please note also that even with 0.1% resistors here in that circuit, we have a common mode error of a maximum of 10 millivolts at the output, which corresponds to 0.06 volts at the input. So depending how our results are, I will have to switch out these resistors for even more precise ones. And I made a video about these common mode error stuff in differential amplifiers quite a while ago. Card here, link in the description. Fourth, for the temperature measurement, I'm no longer using a PTC thermistor. Instead, I'm using here a temperature sensor with an analog output, basically a shunt voltage reference that changes its voltage with temperature. And that solves our output impedance issue here. It also simplifies the software because we have now an output voltage that is directly proportional to the temperature. The 3 op-amps are all in the same package as a quad op-amp, and here's the power supply for that quad op-amp, and the 4th op-amp, we might use that in the future. What I haven't implemented yet is the linear regulator for all the analog stuff. We might do that in the next video. You'll see why. For more details on those solutions, their pros and cons, see the previous video. Here's how everything looks on the breadboards, and yes, things changed considerably. The 2 breadboards changed places. So the one with the power supply was last time on the other side, and it also contained our RS485 transceiver, which is now on this breadboard here together with the Arduino and our digital to analog converter driving the motor. Our analog to digital converter was before located where our RS485 transceiver is now. And here's our quad op-amp. Now let's zoom down on this area here. Our reference voltage comes here through the green wire from our current sensor and goes directly here into the input of the first op-amp, which buffers it, and then it comes out here through the other green wires and is distributed wherever it's needed. The red wire here brings over the battery voltage from the connectors, and these 1, 2, 3, 4 resistors together with that little Zener diode are the circuitry for the other op-amp here, and the output is jumped over here into one input of our analog to digital converter. The other 4 resistors here form together with the second op-amp on that side the differential amplifier for the current signal, here coming in with the yellow wire. And that's jumped, you can barely see it, with the green wire to another input of our analog to digital converter. That 100 nanofarad capacitor here is just decoupling the power supply of our quad op-amp. The TO92 package here is our new temperature sensor, and together with these 3 resistors it creates a temperature signal which is fed into the next input of our analog to digital converter. The stuff here is our intrusion detection, which feeds into the last input of our analog to digital converter. And that's basically is the new analog front end. 2 remarks. The inputs of the unused op-amp here are, well, positive is bound to plus 5 volt and negative is bound to ground, just to keep anything from oscillating here. And that red tape here is just to make sure I don't get stupid and plug that 24 to 30 volt line somewhere where it doesn't belong. Yeah. You might have noticed that the motor leads are not connected, and instead I have here inserted a copper short between the outputs of the current sensor boards. That's because in the next step we will calibrate the current stuff. And you also see here two more wires creeping into my power supply because while I'm shorting out here the battery rail, I cannot supply power from our usual power supply to my power supply. Instead, to power up my power supply, I'm using another power supply. That's a lot of power supplies, huh? And here in the basement you see that additional power supply and the wires going up here to my breadboards to temporarily supply my power supply with power. Before we go any further, let's check some basic voltages. First here, the 9 volt voltage out of my switch mode power regulator, switching on the external power supply, and it's 8.955 volts. That's perfect, and that's going into our Arduino. So our Arduino power rail should now be at 5 volts, 4.934, that's also good. The reference voltage coming from our current sensor, where can I get it? About here. That should be 2.5 volts, 2.502. That's within limits. And where can I get my buffered reference voltage? Yeah, about here. Okay. 2.502 volts. Yeah. That was one of the reasons I choose an op-amp with a very low DC offset at the inputs in the microvolt range. So we get actually the same voltage out we put in. And now a little test where we saw last time that our reference voltage rail bogged down. I'm shorting out here the intrusion detection and well, absolutely nothing happens. Perfect. So that part of the new circuitry works as expected. And here's how the whole thing looks on the serial monitor. Let me stop the scrolling here. And as you can see, we are at 0 amps now. And we get values around 2048, which is perfectly fine, because at 0 amps, our differential amplifier should output 0.25 volts, exactly the center value of our dynamic range. And I will do a min-max analysis here of the values, so the noise peak to peak, the noise RMS, and the average value. But as you can see, since we are already taking a sample of 2048 values to calculate these values here, it's pretty stable. So let's get auto scrolling again and go to our second calibration point, which would be 5 amps. And of course, we see a change here. I saw just a digit flip here. Give it another second until it's really stable. Yeah, 5.007 amps. Yeah, let's believe that for now. Stop again here. Yeah. Looks good to me. As I said, I will do offline on min-max center value analysis of that data too. Let's move on to the voltage calibration, shall we? Okay, now we're calibrating for voltage. I just changed the channel. We are sampling to the voltage channel. And at the moment we are at 0 volts, where I don't want to calibrate, but I want you to note that our average is 1.1 LSBs, not 0 LSBs. That's because the headroom of our op amps, it doesn't go down to ground with the output. Anyway, first calibration point will be 20 volts, and we switch on, and yeah, let's wait a while until it has stabilized. And again, we have lots and lots of noise. And yeah, the motor is still not connected, okay? And so much noise. I have no idea where that's coming from, but maybe we have a solution for that later. Anyway, let's stop the auto scroll so I can do an analysis of the data later. And we're going up to 29 volts. So 29.01. And yep. Let it stabilize. Take a snapshot and yeah. Perfect. And now we do the same for the temperature channel. Again, I changed the channel we are sampling in the code. And we only do a single point calibration here. You see I'm measuring the temperature now, and only, yeah, you cannot probably see it, but there's my temperature sensor from the multimeter, and there's our new and improved temperature sensor. And looking at the data, I noticed that the noise levels are much smaller than for the voltage channel and the current channel. I have no idea why. Okay, I have my data, but let me try one more thing. If I switch on the external power supply, which is really just going to the board and doing nothing. Yeah, not much happening here, is it? Maybe, no, that's not significant. Yeah, anyway, let's analyze the data now. Here are the results of our, well, it was not really a calibration because we were just looking at the raw ADC values and not at the oversampled values we will be using later on. But anyway, we have here the two lines for our current measurements, 0 amps and about 5 amps. The two lines for our voltage measurements, 20 volts something and 29 volts something. And the fifth line is our temperature measurement at 22 degrees C. Our Arduino calculated for us the average LSB over 2048 samples, the noise peak to peak and the noise RMS. And the min and max columns here is basically the min and max of what you saw of these values on the serial monitor. And as usual, I entered the center value between min-max and the differential between the min and max value we saw for all these three values. When we are looking at the values itself, you first notice that the difference, and we forget about the center values for now, between the min and max values are quite low. I'm not saying they are all good, but they are quite low. So we have only a little drift between our samples. I would say everything below 1 LSB, so the last two lines here, that's really good. But everything here above 1 LSB, especially those 5 LSB difference here, that's questionable. If we look at the noise values, that's a whole other story. So here for the current measurements, we have a noises peak to peak of about 250. That's about 5% of the dynamic range of our ADC, or with 50 LSBs per amps, that's about a noise of 5 amps in our measurements. The RMS noise is a bit lower, of course, but it's still in amps about 1.5 amp. Things look a little bit mixed for the voltage measurements, where we have, here a noise level above 5% of the dynamic range of our ADC. And this is maybe 2-3% of the dynamic range of our ADC. But here, those higher values, and we are doing here 273 LSBs per volts, that's a volt of noise in the end in our measurements. Again, the RMS values are of course much lower. The lowest noise levels we have actually for our temperature measurement. It's still quite high. Here 100 peak to peak, 20 RMS, and peak to peak, that 100, that is with 10 LSBs per degree C, about 10 degrees C. So all in all, the noise values are terrible. But where is all that noise coming from? My theory, unproven at the moment, is that it's the 5-volt rail from our Arduino. And now here comes the silver bullet, hopefully. We will now implement the linear voltage regulator here to create a 5-volt rail, linearly regulated, for all our analog stuff. And there's not much to it. We take the LE50AB linear regulator, which we already talked about in the previous video. We put a 10 microfarad capacitor at the input, a 10 microfarad capacitor at the output. The input is of course supplied by our 9-volt rail, which also comes from a switch voltage supply. And we take the 5-volt output to power everything on our analog side. Little errata here. In the previous video I mentioned that the LE50AB is one of the few linear regulators that specifies the supply voltage rejection for higher frequencies. In that case, 60 dB at 10 kilohertz. That's not true. There are other better linear regulators that even specify it up to 40 dB at 1 megahertz. But that one was available in a through-hole package for the breadboard. That's why I choose it. And here the usual breadboard view. So here is our new linear regulator with the 2 capacitors supplying now from our 9-volt switch mode regulator 5 volts to the 5-volt rails of this breadboard here. And please note I created here at the output of the 9-volt regulator a star point. And one line from that star point goes into the voltage input of our Arduino Nano, and the other star point is going into the input of our linear regulator. So the different currents here don't interfere with each other on the same line. I also created kind of a, as far as I could here on the breadboards, a star point for the ground. Let me adjust here just a little bit. So here that black line, that's our ground coming over from the from the current sensor. And then from there we have that ground rail here for the analog side, and then at approximately the same point I'm jumping over ground to the other breadboard for the Arduino and the rest of the ground. I mean, it's still the same ground, but we have a star point now here, so that currents from that side and that side don't interfere with each other. The last measure, last action I took here was I took the digital ground from our analog to digital converter, and that is no longer connected here to my, let's call it the analog ground plane, but is now directly jumped over here to my, let's call it digital ground plane. Yeah. Now we'll see how that performs. But before that, as always, you shall check voltages. Now I'm measuring here now our new analog 5 volt rail, which should be within 1% of 5 volts, which it is. Now I'm switching over here to the Arduino 5 volt rail, which is also good, 4.95, but still not as spot on as our analog one with 5.012. Anyway, the main thing is that hopefully our new analog rail is now quieter. Okay, let's do the test the other way around so I don't have to change the code. So we are still measuring temperature. What's going on here? So my noise is now between 56, which is a lower noise, yeah, and somewhere in the thousands, 3,600. What? Something's terribly wrong. Okay, I added here a serial print, printing out our sample we are taking here inside our sample block, just to have a look really at the raw unprocessed data from the ADC. Let's try that again. Okay, this is of course now quite flickery, so let's stop the auto scroll and have a closer look. So, for example, here it says noise 1856. So, and if we scroll back and have a look at the values, they look good. Do I have somewhere, I don't know, a bug in the software? Looks normal to me. Looks normal. Oh, do you see that? 3,616 in between. Okay. That's interesting. And here again, 3,618. 3,629. That's definitely another number. So we do have a problem. Either the ADC gets at its inputs voltage spikes, or the ADC for some reason gives us crazy values in between, or we got some bit flips between the ADC on the SPI line, between the ADC and our microcontroller. Curious. So we obviously have some intermittent errors, but I think we have a much deeper seated problems. Remember, just a few minutes ago I told you these noise values, the peak to peak, are terrible. Well, the RMS are of course also terrible. Do you remember the last time when we looked at raw ADC values? Yeah, I went back in time, and remember, we are talking here a few hundred LSBs peak-to-peak noise. In video number 6, card here, link in the description, we took for the first time raw ADC readings for current measurements. And as you can see, we had a few LSB noise. And now we have almost 2 orders of magnitude more noise. That's wrong. And in video number 9, a card here, link in the description, we took for the first time raw ADC values for the voltage measurement. And again, okay, this was with the motor on. So with the motor on, we got 16 LSBs of delta or peak-to-peak noise. With the motor off, 6 LSBs of noise. What's going on here? Okay, so I have a lot of theories what's going on, but absolutely no data at this point to back them up. And so the only reasonable way forward is to undo all the incremental changes we did since video number 9 to identify that crazy source of noise we have. And those intermittent errors, they are a whole other issue. Maybe they disappear if I can isolate the noise source. Anyway, that's it for today. I hope I have better news next time. Till then, bye.